So we are now in the home stretch of our study of pre-calculus, and we're now to begin to study trigonometric functions. So there are two parts of trig functions that we're going to study. First, we're going to actually introduce the trig functions. We'll look at properties of trig functions and graphs of trig functions. We will then move into what's known as analytic trigonometric functions. And this is where we will really delve into the properties of trig functions. So we'll start by introducing the trigonometric functions as well as looking at some of their properties. And we do this by first looking at what an angle actually is. So we start by looking at a ray, and a ray simply consists of one point on a line and all points extending in one direction from that point. So this figure is an example of a ray. It starts at the point E and it includes every point in one direction from E. Now, sometimes this will also be called a directed line segment. All right, line segment in the sense that it's not an entire line, and directed in the sense that there is a specific direction to this segment. Now, in this figure, we can see that E is the starting point, and we call this the end point of the ray. So we refer to a ray by stating end point and any other point on the ray. So from the figure, we would denote this as ray EF, or simply like this, EF with an arrow over it. Now an angle is simply the union of two rays that have a common endpoint, as we can see here. So in this figure, the common endpoint is again E, and we call that common endpoint the vertex of the angle. The two rays are called the sides of the angle. And in this figure, the angle is formed by the rays EF and ED. Angles are named using a point on each ray as well as the vertex. So this angle would be represented as angle DEF, or simply in this notation. Often we represent an angle with just a single Greek letter. Common Greek letters that are used are theta, phi, and psi. Most commonly theta and phi. Now also, we represent an angle in a figure like this by typically drawing a line, a curve like that, and then we would write in here what the angle is. So again, commonly it's theta, so we would just write theta there. Now, angle creation is a dynamic process. So in order to form an angle, we begin with two rays that lie on top of each other. Then we take one of the rays and begin to rotate it about the vertex while holding this other ray constant. The ray that is held fixed is known as the initial side of the angle, and the ray that gets rotated is known as the terminal side of the angle. We indicate such rotation with a small arc and an arrow that points to the terminal side, or as mentioned before, we will often just not use the arrowhead. Well, now we come into the problem of how do we measure an angle, right? So there are many applications for angles, and in order to use them correctly, we must be able to actually measure them. So the measure of an angle is defined to be the amount of rotation from the initial side to the terminal side. And we have two common measures. The first is known as the degree, and it is defined to be 1/360th of a circular rotation. This notation is represented here, right? So for instance, 90 degrees be 90 degrees. So to formalize our work with angles, we will draw them on an XY coordinate plane as shown here. Now, while the angle can occur in any position, it is convention to illustrate them on the same position whenever possible. And we call the most commonly used position the standard position. And an angle in standard position has the vertex as the origin and the initial side as the positive x-axis. If the angle is measured counterclockwise from the initial side to the terminal side, as shown in this figure, the angle is said to be a positive angle. So the angle will have a positive magnitude. If instead the angle is measured counterclockwise, so we rotated it this way instead, then the angle is said to be a negative angle, right? It'll have a negative value. And since we draw the initial side along the x-axis, we have special names for those angles whose terminal side lie on an axis. These are called quadrantal angles, and there are 4 of them. We have 0 degrees, in which the terminal side is just on top of the initial side. 90 degrees is where the terminal side is the positive y-axis. 180 degrees is where the terminal side is the negative x-axis. 270 degrees will be where the terminal side is on the negative y-axis. And returning to the positive x-axis will be 360 degrees. So let's go ahead and sketch 2 angles. We'll sketch 30 degrees and negative 135 degrees in standard position. Right now these are just sketches, right? So they don't have to be perfect. So we have XY plane. Let's actually draw these on the exact same axis. So put this in the middle. Right, there we go. Right, so we'll call this our x-axis, we'll call it y-axis. Right, so for 30 degrees, well, this is 0, this is 90. So 30 is going to be somewhere in here, and it's going to be closer to the 0 side. So maybe something like, maybe something like that. Right, and we'll call this 30 degrees. You can use a different color, let's use yellow, to draw the negative 135. So if we're going negative, right, so we have to go counterclockwise, so 0, negative 90, negative 180, and we're looking at negative 135. So that's going to be somewhere that's halfway between. So it'll probably be, something like this maybe. No, let's do more like this. Let's say. Right, and the rotation went around this way, and this is negative 135. So the second common measure is known as the radian. So recall that the circumference of a circle with radius r is given by 2 pi r, right? The circumference of a circle is 2 pi times the radius, where pi is a fixed constant and typically is taken as 3.14. Dividing both sides by r will give us c over r is equal to 2 pi. So what this is telling us is that the ratio of the circumference of a circle to its radius is 2 times pi. In other words, this ratio is a constant. So the ratio is 2 pi regardless of whatever the length of the radius is. This is what allows us to define the radian. 1 radian is the measure of a central angle of a circle that intercepts an arc equal in length of the radius of that circle. A central angle is an angle that is formed at the center of the circle by 2 radii. So as we can see here, we would call this T1 radian because this length here is the same as the radius. Now, since the circumference of the circle is always 2 pi r, we conclude that the measure of an angle formed by 1 full rotation would be 2 pi radians. So if we started here and we rotated all the way back around to here, right? So we had, let's do this in red. So we did this and came right back to where we started. No, that's awful. That looks better. Then this would be equal to 2 pi. Furthermore, since an angle formed by 1 full circular rotation is also 360 degrees, we must have that 2 pi radians is equal to 360 degrees. So this allows us to find conversions from radians to degrees and vice versa. Those conversions are 1 radian is 180 degrees divided by pi, and 1 degree is pi divided by 180. Now it is important to note that the radian is actually dimensionless. Right? That is, it's not really a unit. It is used more as a placeholder. Right? Because if we say the angle is 2 pi, that doesn't really sound right. So we'll say the angle is measured to be 2 pi radians. However, the radians is not really necessary. So right here, I actually don't really need to write that. I could just write this as 1 is equal to 180 degrees over pi. But that just does not sound right. That's why we would say 1 radian. Now we want to convert these angles from radians to degrees, so we'll start with pi over 6. So we'll write pi over 6 times the conversion from radians to degrees, which was 180 degrees over pi. So the pi's would cancel each other out. And we'd be left with 180 degrees divided by 6, which is 30 degrees. All right, finally 3 radians. So again, 3, then we have times 180 degrees over pi. So 3 times 180, we'll have 540 degrees all over pi. And then we just have to approximate this using technology, and this is approximately 171.89 degrees. Right now, in the future, when we're looking at applications of angles, I would just leave it in this form, leave it in the exact angle. Now we wish to convert 15 degrees to radians. So we start with 15 degrees. We multiply by the conversion into radians, which is pi over 180 degrees. Now, the units will drop out, so degrees drop out. We're left with 15 pi over 180, which is pi over 12. So we were talking about length of an arc before. We're going to study this now more in depth. So an arc length, S, is the length of a curve along an arc. So the arc length of an arc of a circle produced by any given angle has a constant relation to the radius, regardless of the length of this radius. From the previous discussion, we conclude if the length of the arc is S, then the central angle would be theta is S over R. And so the length of the arc that is subtended by a central angle of theta measured in radians is S equals R times theta. And this is really important, this in radians. Right? So it's so important. I'm not only going to underline, I'm also going to highlight it. In radians. This formula only holds if the measure of the angle is in radians. If it's not, if you're given the angle in degrees, then to use this formula, you would first have to convert from degree to radians. So let's assume that the orbit of Mercury around Sol, which is the name of our sun, is a perfect circle. And now this is actually a really huge assumption. Anyone who has studied astronomy knows that the orbit of planets around stars, specifically our star, so the orbits of our 8 planets around our sun, are not actually perfect circles. They're what's known as an ellipse. However, for Mercury, it is fairly safe to assume it's a perfect circle because the ellipse is so close, this ellipse is so close to a circle anyway. Now, Mercury is approximately 36 million miles from Sol. In one Earth day, Mercury completes 0.0114 of its total revolution. How many miles does it travel in a single day? All right, so we need to first find the length, right, and let me just specify that right now we are working on A. So the length of the orbit, so we take 2 pi, right? So essentially what we're looking for is circumference, right? If this is our sun up here, let's say this is Mercury, orbits in the perfect circle. Right, the length of its orbit is that line that I just drew, that circular line, which is of course circumference. So that's 2 pi times 36 million. And I'm going to use scientific notation here to write 36 million as 36 times 10 to the 6th. Right, so this would be 72 pi times 10 to the 6th, which is approximately 226 million miles. So in one full revolution around Sol, Mercury travels about 226 million miles. Now, in one Earth day, Mercury, I don't know what happened there. There we go. In one Earth day, Mercury is said to travel about 0.0114 of its total revolution. So we would take 226 million miles and multiply that by 0.0114, and that will give us about 2.5764 million miles. So in one Earth day, Mercury travels about 2.5764 million miles. We now want to look at part B and determine the radian measure for Mercury's movement in one day. So we're now working on part B. Right, so remember, if I go back to this example here, let's just say 0.014, let's say that's this here. Right, so we're looking for this length. Or, I'm sorry, we're actually given this length, right? This length is the 2.5764 million miles. What we want to do is find that angle right in there. Let's call it theta. Right, that's what we're trying to find. Well, this is obviously going to be an arc length. Right, so we're going to use S is equal to R times theta. Since we're looking for theta, we solve for it, and we get theta is equal to the arc length over the radius. Now, the radius was given to us. Right, it says that Mercury is about 36 million miles from Sol. So theta is equal to S, which was 2.5764, over the 36, and this will give us about, or actually an exact answer of 0.0715, and then 6 repeating radians. Now, when a central angle is formed, not only do we get an arc, but we also get what's known as a sector. So think of a pizza. Right, so I'm just going to draw something up here. That was all. It doesn't have to be a pizza, anything round, a cake. Right, so here's our pizza. Now, typically we slice, or a pizza is sliced into 8 slices, right? We have, say, let's do it this way. It's the easiest way to slice it. Right, so typically you get your pizza and it will come in like this, right? 1, 2, 3, 4, 5, 6, 7, 8 slices. Each of these slices is a sector. So if I just shade in one slice, so let's just look at this one, that is a sector of the circle. Now a sector has a certain area. Recall that the area of a circle of radius r is given by pi r squared. So if two radii form a central angle theta measured in radians, again, that's very, very important. Central angle must be in radians. Then theta over 2 pi is the ratio of the angle measure to the measure of a full rotation. And so would also be the ratio of the area of the sector formed by these two radii to area of the full circle. So we would thus have that area of the sector would be theta over 2 pi times pi r squared, which is theta pi r squared over 2 pi. The pi's will drop out, and we have 1/2 theta r squared. So this right here is the area of our sector. So an automatic lawn sprinkler sprays a distance of 20 feet while rotating 30 degrees. What is the area of the sector of grass that the sprinkler waters? So if we look, let's say this dot here represents our sprinkler. So it's going to rotate 30 degrees. So let's say this is the full range of its rotation. And we know that that is 30 degrees. We also know the distance it's spraying, which is 20 feet. All right, so area is 1/2 theta r squared, right? So theta needs to be measured in radians. So I can just do the conversion all at once. So 1/2 theta r squared. So we're going to have 1/2. Now 30 degrees times the conversion factor, which is pi over 180 degrees. Then times the radius, which is 20 feet squared. So it's 1/2 times pi over 6 times 20 squared is 400, so 400 square feet. So this is 1/2 of 400 is 200, right? And then 200 over 6 can be written as 100 over 3. So we get 100 pi over 3 square feet. And if we approximate that to get a better idea, that is about 104.72 square feet of grass that has been watered. Now recall that one full rotation is 360 degrees or 2 pi radians. While larger angles and negative angles are possible, it is convenient to work with angles in the range of 0 to 2 pi. So coterminal angles are angles in standard position that have the same terminal side. When studying trigonometric functions, which we will begin doing in the next video, it is convenient to work only with acute angles, that is, angles that measure less than 90 degrees. An angle's reference angle is the measure of the smallest positive acute angle formed by the terminal side of an angle and the horizontal axis. So, in other words, when we look for a reference angle, right, let's say this is our angle right here. Our reference angle is the angle that is measured with the horizontal axis, the x-axis, regardless of whether it's the positive or negative. Right, the coterminal angle, so what's drawn in white right now is the coterminal. We could do this, right? We could do one full rotation and then rotate around, right? So this red would be an angle that's larger than 360 degrees. The coterminal angle would be what's drawn in white, just the one rotation. So you take away a rotation, basically. Right, so for the following angles, we're going to find the coterminal angle phi, such that obviously phi is between 0 and 2 pi. That's the definition of coterminal. So start with 800 degrees. So remember, we're looking for an angle that is between 0 and 2 pi, or 0 and 360. So the first thing we should do is subtract out 360 degrees and see what we're left with. So that'll give us 440 degrees. Right, that is still not between 0 and 360, so subtract out another 360. That'll give us 80 degrees. Now that is between 0 and 360, so we take our coterminal angle phi to be 80 degrees. Right, so 315 degrees. Now, that is already between 0 and 360, so that would be our coterminal angle. So our coterminal angle in this case happens to be the same. And finally, if we look at 19 pi over 4, so again, we're looking for something between 0 and 2 pi. Well, 19 pi over 4 is larger than 2 pi, so subtract out 2 pi. That leaves us with 11 pi over 4. That is still larger, so subtract out another 2 pi. That'll give us 3 pi over 4. Now that is between 0 and 2 pi, so our coterminal angle here is 3 pi over 4. We will look at reference angles more in depth in the next video when we study the trigonometric functions. For now, that concludes our study of angles. As I said, in the next video, we will begin studying the trigonometric functions.